In this screencast, we're going to look at the effect of a diluent on the equilibrium conversion for a liquid phase reaction. In particular, we're going to look at the case where we have an exothermic reaction, and the reaction is A goes to B. We have a solvent present, which is the diluent, and the reactor is adiabatic, and that's an important aspect of this. So the question is, how does the equilibrium fractional conversion of A change as the concentration of A decreases or as the concentration of the diluent increases? So what we want to look at is a plot of fractional conversion versus temperature to give us a better idea of the behavior. So this is how the equilibrium conversion, it decreases as temperature increases for an exothermic reaction. And now if we look at an adiabatic reactor, essentially for an adiabatic reactor, the conversion is directly proportional to temperature, or the conversion is proportional to temperature change. And so if we look at the energy balance for some starting temperature, the behavior is going to be along this line. So our starting temperature at zero conversion, our equilibrium conversion, so this is an adiabatic reactor. And this is one where we have no diluent. So the question is, as we add diluent, what happens? Well, what's going to happen is we're going to have more material we have to heat up, not just the reactants and products, but also the diluents in an adiabatic reactor, which means the reactor does not get as hot for the same conversion. So what this means is the curve is going to look something like this. The same starting temperature, but now notice at a given conversion, the temperature is lower because of some of the energy from the heat reaction went to heat up the diluent. If we add even more diluent, then the curve, again, same starting point. And so this is the effect of diluent on the conversion. So we conclude that the equilibrium conversion increases as the concentration of A, the starting concentration, or we could say in the feed, depending on the type of reactor, that starting concentration decreases and the diluent concentration increases, then we have higher equilibrium conversion. So we look at the energy balance to see where this comes from. If we say we're running a steady state flow reactor, the heat reaction, and then the fraction of the feed that's converted, well, that's the term for reaction. And then we have the term for the heat capacities, the heat capacity of A, the heat capacity of B, and the heat capacity of our diluent, of our solvent, our unreactant solvent, same thing. And then the temperature minus the starting temperature, so T0 is here. And so we've written the energy balance. This is the heat of reaction, the conversion, the molar flow rate, moles per time into the reactor. Now the heat capacities of each of the species, and then the temperature difference between, say, the inlet and the outlet. And we should check the signs. This is exothermic reaction. This term is going to be negative. This term is going to be positive. Temperature goes up, so everything is consistent. And we can see as we increase the amount of solvent, because for this equation to be correct, we have to add the flow rate of A, the flow rate of B, and the flow rate of solvent into the equation. And as we increase the flow rate of solvent, then we decrease the temperature increase due to reaction. So in practice, we could certainly do this to increase equilibrium conversion, but it has some clear downsides. Now the kinetics of the reaction are slower because we've decreased the concentration of reactant, and most reactions are proportional to some power the concentration of the reactants. We also have more material, more feed to actually process. And we have now created a more difficult separations because we have to separate the products and the unreacted reactants from the solvent. So there's a trade-off between these, and as usual, economics determines how we would do this. But this shows what the effect of diluent is for liquid phase reaction.